next up we've got Mike Greenwood from CGI, and he's a data scientist, so he's going to talk about some of the issues around AI and some of the skills needed to address these challenges.
So this one is a little bit less AI in teaching and a little bit more AI in space. So a bit of a 90-degree turn. So my talk is all about the failure of practical data science in business. This is a pretty important one because this gets missed a lot. People tend to like teaching machine learning techniques and how to do things, but unfortunately there is still this horrible failure rate. The one thing that I want you to take away from all of this is that data science problems do not yield to reductionism. Note that I'm not saying that data science solutions can't be nice and simple and straightforward and relatively easy, but they must address the entirety of the problem itself. The failure rate of data science projects is absolutely horrifying. I mean, truly horrifying. I could say, what I've put on screen is more than half of practical data science projects fail in real business terms. It's almost certainly considerably higher than that. Businesses do not like to talk about how they fail. They want to come across as nice and trustworthy. They want to say, ah, yes, you can, our solution, you can trust us. It's wonderful, it's brilliant. It works every time. But in terms of things not working, and especially in terms of projects that simply do not meet their available potential, especially on that point, there is a very serious problem. Because of this horrible failure rate, businesses tend to have a real trust problem. That tends to manifest in kind of a, we need to control this. It was a problem with the data scientist. It was a problem with the data. It was a problem with some other thing that we can then consume into our wonderful, amazing business practices. And that sort of controlling grip tends to cause all sorts of interesting problems in itself. Kind of the best thing that can possibly happen is kind of two situations. Either a business is naive, they have never experienced data science failure of a project, or they have already experienced a great deal of project failure, and they think, okay, we don't know what we're doing here, and we need to find someone that does know what they're doing. Either way, if you're a data scientist and you're trying to further your career, you need to lead on this. You need to do well on this. You need to seize this, and you need to take it forward in the right way. So let's talk about how things commonly get sold. I can see we have some enjoyment of my simplistic, straightforward, all eyes on me kind of way of presenting things. But yes, if we have a standard client who will look at things from business terms, they will say, okay, data science, AI, because buzzwords, it's a client, it's magic. It does wonderful things for business. And it is currently transforming all sorts of markets, all sorts of sectors, and it's transforming my market and my sector and what my business is doing. That's wonderful. So I've got to get some. I've got to go out and buy some. Let's go and ask for some, and some company, perhaps a new employee or a contractor or someone that is delivering this service will say, yes, wonderful, I can give you this. Absolutely. What do you need? And they'll say, okay, well, this thing makes me a lot of profit. This thing makes me money. Or conversely, this thing is very expensive for me. I want to reduce the expense of this thing, so more of this or less of this, please. And the company says, oh, wonderful. We're a bunch of salespeople still at this point. This is wonderful. All we need to do is consider this thing. So let's assign some data scientists. Let's make a project. Brilliant. We'll see you in 6 months. If you can just go and predict this thing, that's what machine learning does, right? It predicts a thing, right? Everyone knows that. Let's go and predict the thing. Fantastic. And now the project is dead. More specifically, the project is doomed. If you don't recognize that the project is dead, then you experience a very slow death and degradation as we don't actually manage to meet deadlines or some requirement for accuracy or some capacity of the project. Often this manifests in a kind of, well, this does a thing, and it's sort of related to the thing that we want, but it's a bit sort of tangential, it's sort of parallel or perpendicular to kind of what we actually wanted. Or maybe it's just not accurate enough. And often the reason for this is because the problem itself does not yield to reductionism, and throughout a big long chain of communication, the problem has been reduced. So The client has made assumptions about their own problem. They like talking in terms of solutions. Clients like to say, yeah, we want to predict this thing. Do you? You sure? What is the actual problem? Why this thing? Why does this make you profit? Why does this make you money? What does this do? What do you want this to achieve for you? But instead, we end up with a simplification because we like to speak in simple terms. We like to have nice, simple communications. The salesperson has assumed how this problem can be addressed. They also make assumptions about machine learning. There's two horrible ways in which they make assumptions about machine learning. Either they also assume that machine learning is magic, or they assume that machine learning does predictions, which is a very limited view of what machine learning can and can't do. And then you get this to the data scientist, or it gets filtered through. You make project goals on some bureaucratic piece of software that does all of this management for you, and everything filters down, and you've got all of these lovely, deliciously filtered little bits of, should we say, corporate bureaucracy that then you get, the data scientist gets a hold of this, and the data scientist thinks, wonderful, it's so simple. I've just got to predict this thing. And it's exactly like it is in academia. It's exactly like it says on the tin. I've done this 100 times. I've done this in academia. I just have these things that I need to create. I need to train a function approximator that takes in this whole bunch of values, and I've got to predict this thing. Brilliant. It's a lovely, clean problem, exactly what I'm used to in academia. And the right questions are not asked. We don't actually get to the things, to the crux of the problem itself. Data so it's all a big, complicated ecosystem. You've got Tina in accounting who uses this one unlabeled column in some Excel spreadsheet that you've been given to do your data science on, and only she actually knows what the meaning of this column is. But it's absolutely vital to understanding the actual meaning of the data and what on earth is going on. You've got how the data is actually getting generated. You've got all of these independent systems going on in a business that are all fighting with each other a little bit, but also cooperating wonderfully with each other, and they have all of these truces and understandings with each other. And very, very crucially, we have how the data science project will actually get used. We get real power in business in data science when the shape of the problem is met with the matching shape of solution. We'll get on to what on earth this means, because I'm talking very much in the abstract, aren't I? And I'm sure a lot of you can think, yeah, I get the gist of it, don't quite actually understand what that means in real terms. We will be getting to some examples. What often happens is an engineering view. There is a top-down idea of, okay, this is a thing we are making, this is a thing that we need to perform some task, this is made of components, and we will split it up into lots of different components, and this is the data science component. We will deal with that particular data science component independently. This is horrifying and will always lead to some unfortunate results. If you are being split up into a part of a machine and you are being sort of plugged in to something else that is achieving some wider purpose that you are told not to worry about, be concerned. So let's go through some actual examples. Let's go through a childlike as an example to start with, just to show the real most common problem here. And so this happens all the time. Here we have an ice cream stand, which is unbelievably wealthy. They sell their ice cream for £1,000 a scoop, and they have enough money that they actually want data scientists in. They're interested in the number of customers that they have, and there is a discussion with salespeople, and the discussion comes out as, okay, we want to predict the number of customers that we're going to get. Fair enough. This is a bit interesting because the customer doesn't actually want to predict the number of customers. They're not actually trying to predict what will happen if I have these circumstances. What they want is to increase the number of customers that they have. They want to affect a value. They are maximizing a value which is different from predicting a value. And therefore, we have all sorts of weird nuances to this, because by definition, what we are trying to achieve is some state where we get more customers than we've ever had before. We are by definition outside of the training distribution, by definition. We're also having all sorts of weird issues with, okay, well, let's say we've got some number, we've really simplified down, of the number of other ice cream stands that are out that day, how many people we are competing with. And you've only got a few months of data, and you've got always 3 competitors. That value doesn't change. No approximator will say this changing this number will have a significant effect on the number of customers that you actually get. So when you actually need to say, okay, we need to hire the mafia and take out a hit squad to destroy all the competition, you can't give that wonderful, useful advice, because as far as any of your approximators are concerned, this thing has no effect, even though it does have a very significant effect. The value that they're interested in is also likely subtly different from the value that they actually asked for. So we could say, for example, we have 100 customers, 1,000 customers that turn up in a certain place in one day, and we could be asking instead about the proportion of customers that we're actually getting. So how many of the whole are we getting to our ice cream stand as compared to other ice cream stands, which could remove some confounding factors, which could be extremely useful. And so we might want to ask subtly different questions to our machine learning approximator, to the thing that we are training to deal with this. We might want to ask, okay, how many customers are we going to get? Or instead, we could design an approximator, we could train an approximator to learn, okay, what is going to be the change in the number of customers from this change in circumstances? You might think, well, that's the same thing. That's the same approximator, you're doing the same thing. You're not. That is subtly different, and you will end up with different results. And often, for this sort of thing, where the customer doesn't quite know what they want, you often want to ask a whole big smattering of questions, and then you compare the approximators and what they're doing, and that will often get you most of the way there. So I'm going to talk about an actual proper thing that we're doing called Project Seagrass over at CGI. Seagrass is grass, what is under the sea. It's very, very useful stuff. It drinks in carbon. It's a keystone species. It's used as food for a bunch of different things. A bunch of different sea insects live in it. It's lovely, lovely, lovely stuff. And the initial thoughts for this was, so this was partnering with Project External CGI, where there's a conservation effort going on. We want to know where the seagrass is. Tell us where the seagrass is. Currently, it's at an infrastructure stage, where there's sort of this understanding of, okay, the input is going to be this data, we know it's going to be this data, we know what we're going to be using, and we know that the output is going to be locations to check for seagrass. And because we can make that assumption, we can make all of the infrastructure ahead of time. This is a fantastic way to do a data science project, by the way, if you can make the right assumptions, and only if you can make the right assumptions. Very recently, okay, now we need to start taking the data science bit seriously. Let's make something amazing. And so we have this long discussion of what are the assumptions, what is the hierarchy of assumptions that we need to traverse and experimentally work with in order to deal, in order to actually solve this problem. And it was first thought to be a classification problem, seems reasonable. It was thought to be a prediction problem in general, okay, yeah, makes sense, we want to predict this thing. And it was thought to be supervised, as in we want to have a certain number of labels, ground truth correct labels. This is seagrass, this is not seagrass, and we want to train a classifier on this. Wonderful, easy. So there was an initial attempt that was based on some other research about rainforests. And thankfully, well, I say thankfully, this is a damn good team, so wonderfully, the infrastructure is extremely flexible and very, very universally applicable. But what gets interesting is that a very small number of tweaks to how the approach is made massively improves results. I mean, massively improves results. So the thing about this is that we have locations saying there is seagrass here. We actually don't have data saying there is not seagrass here. So we can manually say, okay, well, here's a patch that's barren and we can be fairly sure that there's no seagrass here, and we can create labels if we want. We can generate a little bit of our own data in order to deal with this problem of we've got to try and sort of shove it into the supervised learning setting. We've got to shove it into this back propagation type of setting where we want to, where we're learning ground truth labels, or we can do something more interesting. Like we can have a model that is semi-supervised, or we can do representation learning. That means that we have a machine learning system that learns from data that does not have a label associated with it. So it learns from data with labels, it also learns from data with no labels at all, and learns the whole spectrum of all of the data and manages to deal with all of that. Also, the value comes from preserving the meadows. This isn't just a prediction problem. Ultimately, we have to ask that same question. What is this going to be used for? What is the value of this? What does this do? And the answer is that they take a boat and they go out and they check if there's seagrass. and it's very useful in some places, it's not so useful in other places. So this is a resource allocation problem. It's not just a pure prediction problem. And ultimately, our certainty of whether or not this is actually a patch of seagrass matters a lot. If we can check a patch and we can say 100% certain this is seagrass, and that's the result that we get, they don't need to go out and check it. If it's a patch of seagrass is extremely valuable to the ecosystem, and there is a high uncertainty, and it's a huge patch of seagrass, then it's worth them going to check it out. It's a massive resource allocation problem. So certainty of whether or not this is a patch of seagrass or not is almost as important as the prediction of whether or not it's seagrass. Let's talk about a more fun one. Finally, we're in space. This is my project. This is dynamic predictive routing. I'm sure everyone has heard of mega constellations of satellites for routing data. Elon Musk has his famous Starlink that, as usual, overpromises and underdelivers. But enough about that, otherwise I will be here all day. Apologies, seem to be going a little bit over time. Yeah, room full of techies, so it's preached to the choir. So dynamic predictive routing. You've got a mega constellation of satellites, and you want to route data through it. I want an internet connection. I want to watch YouTube. I want to go and get this big bulk download where I'm pirating the B movie. How do you route data through a satellite constellation? So with a terrestrial network, where you're routing data through copper in the ground or optic fiber under the sea or whatever it is that you have, you know what the network is, and the network can be assumed to be static. And if there's a change to that network, you can just assume that new topology to be static. And you can use some very, not basic, but you can use some relatively straightforward algorithms to say, okay, let's route data through here. Okay, there's a lot of traffic over there. Let's route around it. Wonderful. When you've got satellite constellations, these satellites are constantly moving in and out of range of one another. The topology is in constant flux. So how do you deal with that? How do you put data through this thing? Let's work through some of the assumptions and how we're dealing with this. There's no solution. We can't train a function approximator to actually just spit out the right answer because we've given it the right answer and it's just going to learn the right answer. It has to figure out what the right answer is for itself. And yeah, as I've just talked about, the network is constantly changing. And interestingly, we know what the topology changes are going to be. So we can inform the solution, by the way, this network connection is about to break, this one is about to be made ahead of time, and we can say exactly when. A little bit of variation in that because of weather and because you have like some burst of something completely splatting out a satellite, or one of them might just go dead. Any solutions need to be able to interpret that topology, which is an interesting problem in itself because graph neural networks, they have their own issues with things like changing topologies. That's kind of a novel thing that you're going to have to try and represent. And we need to either, one of two things, we either need to find a way to make this a supervised problem, or we need to do it in a completely unsupervised way, i.e. gradient-free optimization. So the way that we could sort of turn the problem inside out is where you could say, okay, this is a routing solution, how well will this do? Or if we make this change to this routing solution, will it do better or will it do worse? And then we can use a simulator to simulate what that routing solution actually does. And we can say, okay, yeah, in the simulation, this does better, this does worse. And we can slowly sort of iterate onto a better solution. That's horrifically compute expensive, which is not fantastic. And also, we end up with some unfortunate constraints on how this can work. Fortunately, we have a novel optimization algorithm that has benchmarked at better than our other options, and we are releasing a white paper hopefully soon, fingers crossed, for novel gradient-free optimization of neural networks. That's neat, by the way. I did that. So let's talk about the actual skills that you need to deal with this. And ultimately, by the way, this is not a matter of covering your weaknesses. This is a matter of amplifying your strengths. That a lot of people will say, well, you've got to do all of these things. These are more just some tips that ideally you need to take this into your own skill set. You need to work this into how you work with business people, or if you are a business person, ideally working on the other side of this, of how you deal with data scientists. Be direct and invite questions. If you say, oh yes, so this model has a multiplicative bias and this one does splitting over the data, so this one can extrapolate a bit better and this one can't, so we might want to think about this because of the other. No one cares. If you say that to a business person, immediately they will have red flags coming up saying, oh goodness, this is more costs to the project. How do I avoid these costs? No, bad data scientist, how dare you? We do not want increased costs. We just want to get to the answer as quickly as we can. So if you say there's an opportunity here, this might cause a lot of problems in the future, and then you just let them ask the questions that they actually have so that you can address their actual concerns, much more effective. Business people talk in terms of risk management. They are risk obsessed in terms of profit maximization. Because we are considering this an engineering problem, people like to think, okay, well, if we have a problem, if we have a risk, first of all, we can define all of the risks up front. No, you can't, it's data science. You can't define all of the risks up front because the risks in data science don't come from, oh, this material isn't quite strong enough, we're going to have to make this reinforcement of this material a bit thicker or stronger or whatever, or we're going to have to work on something else. Or, oh no, this piece of software contains this bug, so we can't rely on this external third-party piece of software or open source or whatever. We're going to have to find something else, find a workaround, whatever. The risks are simply, they don't kill a project. The risks are engineering risks. It is something that you need to work around, something you minimize in a huge, long, forward-looking timescale. In data science, you are discovering things. You are traversing a hierarchy of assumptions that you are exploiting, assumptions that place limitations on what you can do, and assumptions that force your solution into a certain shape, a certain paradigm. Ultimately, you need to be able to communicate that with risk-obsessed people and be able to say, no, it is a risk minimization, it is a good thing, if we have the flexibility to completely change the direction of the project if we discover this thing. How you marry those two together is entirely up to you. It's a difficult one. Good luck. And in general, be very positive and be upfront. Try to talk in terms of opportunities. Oh my goodness, if we create this wonderful foundation where we understand all of our assumptions now, then we manage to create elegant and powerful solutions which are faster to implement and more potent. So we should absolutely create this foundation as solid as we possibly can rather than as quickly as we can, etc. CGI is trying to make this better for everyone. First of all, first angle of approach for dealing with this as a business, we can try and get salespeople to ask the right questions. So we can get data scientists involved in the sales process right up there, right from the start. And we can make sure that no crazy promises are made too quickly. Often this doesn't need to derail things. The important thing is that this is an enrichment of the sales process and doesn't take over the sales process. We don't want data scientists to take over and do horrible, we're data scientists and we know best. No, you don't. We instead want to just have light suggestions of what the right thing might be. And we want to make sure that salespeople understand, hang on, if we don't know this thing, that's something that could either derail everything later, or it might be exactly perfect and fine, and we don't know yet, we desperately need to know this thing. So just little prods and suggestions. When it comes to the data science consideration of the actual problem itself, parallelization is key. This is science, and ultimately it kind of works like having a white paper and having a whole bunch of peer reviews on that white paper. So we are interested in making sure that all of the information about the problem gets exposed to lots of data scientists in isolation of one another, and then everyone can write down what they think are the assumptions associated with the problem. And then for, just to sum that up, we have some very senior data scientists talking to salespeople, and we have a nice back and forth and with a slight direction towards the sales process. All of the information that comes out of this process is then given to a whole wide range of scientists, and all of that is then filtered down and all combined. A lot of this is due to cross-contamination, by the way. If one data scientist on a big call with 150 other data scientists says, I think the problem looks like this, then you end up with hierarchy, you end up with seniority, you end up with the contamination of what people can think about the problem, and we don't want that. We want everyone to think about it independently. So we take all of these independent notes and we distill it down into a hierarchy of assumptions. that hierarchy of assumptions that you then explore with different, you sort of create this plan of attack around validating assumptions that you want to validate, or around disproving assumptions that you want to disprove. And the sort of optimal way to actually traverse that that hierarchy of assumptions is kind of unfortunately a topic for another time, but is very interesting in its own right. To round up, data science problems do not yield to reductionism. You must understand the entirety of the problem, and the solution must actually address all of it. I believe we have 15 seconds for questions. Very sorry about that. Anyone?
I think that was a really interesting talk show in terms of, for us as educators, at least, kinds of things, because again, it comes back to developing critical thinking skills in our students so that they can come and ask those awkward questions.
It's something that is unfortunately very overlooked. You end up assigning very sort of clean versions of data science projects for budding data scientists to learn what they're doing. And ultimately, yes, you can write machine learning models, you can train function approximators, that's wonderful, but ultimately there's a huge amount of people skills needs. There's a huge amount of as you say, critical thinking and being able to deal with all of that. And unfortunately, that's also very difficult to introduce in the classroom, because you need a problem that looks like a real problem, or you need people being, or how to deal with people being difficult and wanting to talk in terms of solutions rather than
I think that's something that we as Sun are really interested in, is to work with industry to give us real messy problems to feed to our students so that they can deal with that. Yes, it's not neat and it won't fit nicely in one class, but if those are the skills they need, then we have to find a way to try and introduce those kind of messy problems to students so that they actually develop those skills.
And unfortunately in business, all of the problems are messy.
Yes, and getting messier.
Yes.
So yes, I think critical thinking and communication to different audiences is the other key thing I think you were kind of bringing out, which is one of the things I think, any of us who are IET accredited or engineering capital accredited, you know that one of the criteria is being able to communicate effectively with different audiences. So it's another challenge, I think, of, if you're talking in business, you have to talk in business terms, not in pure science terms or engineering terms, because they don't understand what you mean, or they just see it as risk.
Absolutely.
So I think, very relevant points to be brought out there for us.
Cool. Thank you.
Thank you very much.